All right, everybody. So in this lesson, we're going to sort of pick up where we left off in the last lesson where we were talking about long division, but eliminate some of the redundancies that we were observing. So you'll notice here on the left, I have literally pasted in an example that we talked about last time. And in that example, we observed, wow, we're writing the same thing over and over and over again, like the 5s, the 27s, the 111s, each got written 3 times, not to mention all of the variables that got written over and over and over again, all of these coefficients that had to be written over a second time. And so what synthetic division attempts to do is it attempts to take out those inefficiencies. So the first thing that we need to do here is we need to define the synthetic form of a polynomial. And the idea here is, if we write terms in decreasing order by degree, meaning the highest degree term goes first, we really only need the coefficients. So all that the synthetic form is just a list of coefficients, including skips. So what I mean by this is that if we skip a term, we don't skip it in the synthetic form. We put a placeholder 0, just like we did in those examples in the last lesson. So for example, just looking at what we did in the last lesson, the synthetic form of 5x cubed minus 7x squared plus 3x minus 7 is, and then I like to separate with something, semicolons, you can do commas, it really doesn't matter, because I don't ever want to accidentally think that that negative 7 and that 3 are actually a negative 73, right? I want it to be very, very clear. So notice that, and we'll actually see an example of this in 1 second, if you were to want to reconstruct this, you could say, well, the negative 7 is the constant term. So in fact, let me write that. So it's almost as though we're now developing this positional system of thinking about a polynomial, that the rightmost term is the constant, then the x term, then the x squared term, then the x cubed term, and so on. So this one doesn't have anything beyond x cubed, but we could keep going. All right. Now, synthetic division. So let's divide. Now, we've already done this, which is nice because it means that we can look back and check our work. So we're going to go ahead and divide 5x cubed minus 7x squared plus 3x minus 7 by x plus 4. There's 2 ways of approaching this, and I prefer the first one myself, but it's not because it's more correct. I just think it's more intuitive. So I'm going to show you the way I prefer first, and then I'll show you the other way as well. So we don't write the whole polynomial. We just write its synthetic form. And then here, since we're dividing by x plus 4, we're going to write negative 4 in this little box. Why negative 4, you might ask? Well, remember, what this is all ultimately boiling down to is finding roots of polynomials. And what we're doing here, in a way, is we're checking to see whether negative 4 is a root of this polynomial. Since if negative 4 is a root, then x plus 4 is a factor. If that doesn't ring a bell, go back a couple lessons and look at the remainder and factor theorems. All right, now, check it out. Look at how quickly this is going to go. Just like we noticed in the last lesson, when we're dividing by x plus 4, the leading term of the polynomial we're dividing is going to be the leading term of our quotient. So the 5 just drops down. And now we start a cycle. I call this cycle the multiply-add cycle. I'm not going to do the dotted lines every time, but I'll do it the first time. So I multiply 5 by negative 4. I get negative 20, and then I add. So negative 7 minus negative 20, negative 7 plus negative 20 is negative 27. And then repeat. So again, I'm not going to do the dots again, but look, negative 7 times negative 4 is positive 108. Add, we have 111. 111 times negative 4 is negative 444. Add is negative 451. Well, we're done. This is our remainder. And sure enough, you can look here at the example from last time, and that is in fact our remainder there. And this is the synthetic form of our quotient. So we do have to reconstruct from the synthetic form to an actual polynomial, but we know how to do that. We talked about the positions a little bit above. So, look, even before we reconstruct it, we can see that it's right. The coefficients in our quotient are 5, negative 27, and 111. And there they are. So we did, in approximately 20 seconds, what took us like the better part of several minutes in the last lesson. All right, before I write it all out, I just want to show you, and I'll tell you why some like textbooks and people prefer this. You could have written, instead of negative 4 in this box, you could have written a positive 4. So some people will tell you, well, that makes more sense since it's x plus 4 that this 4 be positive. Okay, sure. And then you again write the synthetic form. And then everything is the same, except in this approach, rather than adding the way that we did in the first one, here we subtract. So to make sure that that's very clear, I'm going to go ahead and start by putting the minus sign there. Everything else is the same. So the 5 comes down, and just instead of multiply add, we multiply subtract. So 5 times 4, that's 20. Negative 7 minus 20, oh, that's negative 27. See, so you still get everything the same, and it's literally just a matter of what feels right to you, what is more intuitive. Some of you will find the addition method a little bit more clear. Personally, I always think it's more intuitive and more clear. But if you like the subtraction method better, they're equivalent. They're not. It's not a matter of, oh, this one's more correct. Okay, negative 27 times 4 is negative 108. And then when you subtract 3 minus 108, the two minuses become a plus. So again, it's 111. 111 times 4 is 444. But then we subtract negative 7 minus 444 is negative 451. So you get the same thing. Same remainder, same quotient, and it's just a matter of what feels more intuitive to you. What I would probably recommend, because I'm me, is I would probably recommend that you do it both ways and kind of make sure that you understand and are comfortable with both of them, and then you kind of settle into the one that is more comfortable for you permanently. Okay, let's do a couple more examples. Okay, so the beauty of these examples is that they take very little time. And then over here in this bottom left-hand corner that I've sectioned off, we'll write a summary. Okay, so let's divide, and we'll do one with a skip this time. 7x to the 4th minus 2x squared plus 5 by x plus 1. All right, here we go. So what do we have? Notice that we have skips. There's no x cubed term, so there's a skip between the x to the fourth and the 2x squared. And there's no x term. There's a skip between the x squared straight down to the constant. So when I write the synthetic form, watch carefully. I have 7. That's my x to the fourth term. The next one would be x cubed, but I don't have a visible x cubed term, so I put a placeholder 0. The next is the x squared term. I have that, so I put -2. And again, from negative 2x squared to 5, I again have a skip. So I put another placeholder 0 there, and then finally my 5. As I think I told you already, I really prefer the approach where we're testing it as a root. So if we're dividing by x plus 1, it's as if we're testing to see if -1 is a root. But if you want to do it this way, please, by all means, I encourage you to, on your own, make sure you can get the same thing the other direction. Okay, so this is going to be the multiply add approach. Okay, so the 7 drops down. 7 times -1 is -7. In fact, let me put in the little dots so we see them. So there I multiplied, and now I'm going to add. 0 plus -7 is -7. -7 times -1 is +7. Okay. -2 plus 7 is 5. Okay. 5 times -1 is -5. Add, you have -5. -5 times -1 is +5. Oh, it was going to be so close. For a second there, it looked like maybe it would all cancel out and you'd have a remainder of 0. Oops, I got carried away. But in fact, it's 5 plus 5 since we're adding, and so the remainder is 10. So here is our remainder. And then here is our quotient. So if we wanted, I'm actually going to write it here, the quotient remainder form would be, so what I'm doing here is I'm reconstructing the quotient from its synthetic form. The -5 is the constant term, then the 5 is the x, the -7 is the x squared, the 7 is x cubed. 7x cubed minus 7x squared plus 5x minus 5 plus 10 over x plus 1. So that is synthetic division. So again, the most important thing is practicing these kind of two approaches and finding the one that feels more comfortable for you. And also, when you're writing synthetic form, make sure not to leave out those skipped terms. Sometimes you won't have any skipped terms, like in our first example. But when you do, there's nothing more important than making sure that you include them in the synthetic form. So last moment. Synthetic division allows us to very quickly divide any polynomial by x plus a constant. So if you're thinking to yourself, well, what if I want to divide by 2x minus 7? Well, synthetic division doesn't explicitly work there. There are some little workarounds, there are some tweaks, but that's not what synthetic division is designed to do. So we could even put that as a little food for thought. You'll notice this isn't really something that we end up having to worry about, but this could be something for you to noodle on. Like, what if I want to divide by something that doesn't start with an x, by, I don't know, 2x minus 7? is there any way to use synthetic division? So think about that. See what you come up with. And I'm curious what you think. All right, so that's our lesson on synthetic division. So what we're going to do in our next lesson is we're going to talk about how do you use all of this stuff to actually start to find roots of polynomials. So the next lesson is, I think, a really exciting one. All right, see you all soon. Bye.